Welcome, students. We have seen while analyzing a structure using force method like flexibility method or strain energy method, we need to draw correct free body diagram. By the way, drawing correct free body diagram is necessary for plotting bending moment diagram as well. If you want to plot bending moment diagram, correct bending moment diagram, we must ensure that we have plotted the free body diagram exactly according to the method. So let's understand how to plot free body diagram for some simple structures under our consideration. Let us say one simple structure we'll take into consideration is uh, let us say this simple structure is a frame, portal frame, which is fixed at this end. We'll call this end as A, and which is free at the other end. Let us say this end is free for the portal frame. We'll call this as B, this joint as B, this joint as C, and this joint as D. And let us say this frame is applied with a load of, let us say, 10 kilonewtons at joint B. Let's start with some simple things. I will say that the length of column AB is around 4 meters. Length of beam BC is around, let us say, 5 meters, and length of column CD is again 4 meters. Let's keep it simple. So this is the frame. We need to draw the free body diagram of the particular frame. Let us say I will add one more load to increase the complexity of the problem. I will add one more load. This load, I will say, this is of 4 kilonewtons at the end D, and I'm going to plot the free body diagram. It will give us the complete insight. 4 kilonewton load acting at CD, acting at ND, and then I have to plot the free body diagram of it. Now, my friends, first thing we should remember that as far as possible, we should try to analyze this from free end towards the fixed end, because in that case, we need not calculate the reactions at the fixed end. If it is possible to make the structure cantilever, if it is possible to make it just like this cantilever frame, then we should start from the free end D and come towards the fixed end A. So first I will take member DC as first member for drawing the free body diagram. Now, how to take member DC for drawing the free body diagram? I am drawing it right over here. First member DC, I am drawing the member DC right over here. Let us say this is member DC, this is D, and this is C. In D and C, this is for 4 meters, and the applied load at D is 4 kilonewton. Is 4 kilonewton is the applied load at D. Now I cannot do anything at D because D, the load is 4 kilonewton. That's all. We cannot make any adjustments. What we have done in this process, we have broken this joint C. We have broken this joint C. The joint C exists in the portion BC and joint C exists in the portion CD. So I have broken the structure at joint C. So I have joint C is broken. So whatever are the adjustment of forces I need to do, I need to do it at joint C, because D I cannot do anything because D is now the fixed, or D is permanent. That 4 kilonewton load is acting and there is no other load acting on D. We cannot allow any other forces to act on D as per our will. But since we have broken joint C, we have to balance this joint C. Now, what is the rule? The rule is every free body diagram is under static equilibrium. This free body diagram of joints member CD is under static equilibrium. It will obey all the rules of static equilibrium. It will follow all the equations of static equilibrium. Let me revise. What is the first equation of static equilibrium? Summation of forces in x direction should be equal to 0. For a body in 2 dimension to be in static equilibrium, there are three equations. First equation is summation of forces in x direction should be equal to 0. Second equation is summation of forces in y direction should be equal to 0. And third equation is summation of moment anywhere on the free body diagram is equal to 0. These are the equations of static equilibrium, and every free body diagram will obey that equations of static equilibrium. But at present, we cannot do any adjustments at D. We have broken joint C, so whatever the adjustments are to be made, we will make it at joint C. So if I want summation of forces in x direction to be equal to 0, this is 4 kilonewton acting on the left. So there must be 4 kilonewton force acting on joint C to the right. In that case, summation of forces acting in x direction is equal to 0. That can be satisfied. So now I can say for this free body diagram of member CD, summation of forces in x direction is equal to 0. The second is summation of forces in y direction. There is no acting force at D in y direction, so there is no question of balancing the force at C, but still I will write y direction I need to balance 0 kilonewton because y direction is already balanced. Now, what is the moment? The third equation, we have taken into consideration the first equation, we have adjusted this 4 kilonewton. We have taken into consideration second equation, that is summation of forces in y direction is equal to 0. There is no force, so we have balanced it with 0 kilonewton acting upwards or acting downwards, anything we can do. Now summation of moment about this C point should be equal to 0. So what is the acting moment at C? This 4 into 4. So acting moment is 4 into 4. If I say consideration, the direction is clockwise. Clockwise is the acting moment. If I want to resist that moment, I must resist it with 16 kilonewton meter. This 4 into 4 comes out to be 16. 16 kilonewton meter moment which is acting anti-clockwise. Acting moment is clockwise. To balance it, there must be anti-clockwise. In that case, I can say the structure CD or the free body diagram CD is under static equilibrium. Every free body diagram must be under static equilibrium. What I have done, I have broken the structure in the form CD. I have separated this C in the joint C from BC and CD, that is same joint C. So I have separated this structure CD. I cannot adjust anything at D, so I have adjusted whatever I need to adjust. I have adjusted at C. So I have adjusted summation fx. To get summation fx equal to 0, I need to adjust this 4 kilonewton acting towards right at C. Since summation of forces in y direction is already equal to 0, so there is no need to adjust, but I have adjusted with 0 kilonewton. And acting moment at C is 16 kilonewton clockwise. There must be anti-clockwise moment so that the structure is balanced. So we can say the structure CD or the free body diagram CD is under static equilibrium. Now, my friends, now every member is in equilibrium. At the same time, every joint is also in equilibrium. This joint C in the portion BC is same as joint C in the portion CD. For our convenience, we have broken it at C, but when we are drawing free body diagram of BC, we should transfer the equal and opposite of these balanced forces at member C, then and then only joint C will be under static equilibrium. Every joint is under static equilibrium, every member is under static equilibrium. We have achieved the static equilibrium of member CD. Now let us achieve the static equilibrium of member BC, member joint C. So I'm drawing free body diagram of member BC. This is 5 meters, I know. This is point B, this is point C. And now look at these. What are the red forces? 16 kilonewton meter anti-clockwise moment, 0 kilonewton downward force, and 4 kilonewton acting towards right needs to be transferred as 16 kilonewton meter clockwise moment because joint C is also in static equilibrium. So anti-clockwise moment in the portion CD will be transferred as clockwise moment in the portion BC. Then and then only we can see the joint C is under static equilibrium because this joint C in member BC is same as joint C in the member CD. It is also under static equilibrium. So whatever is the balance that is achieved or that we have received after balancing CD, equal and opposite forces needed to be transferred at joint C in the portion BC. So these 16 kilonewton meter anti-clockwise will be transferred as clockwise, 0 kilonewton downwards will be transferred as 0 kilonewton upwards, 0 kilonewton downwards will be transferred as 0 kilonewton upwards, and this 4 kilonewton towards right will be transferred as 4 kilonewton towards left. So this is how I have balanced joint C. Now I can say joint C is in static equilibrium. Joint C in the portion BC and joint C in the portion CD is the same joint. So I need to transfer equal and opposite. Now, my friends, look at this. In the original structure, this 10 kilonewton load is given acting at joint B. So it is our choice whether to consider it in the portion AB or to consider it in the portion BC. I will prefer it to be considered in AB always, okay, in the column always, instead of considering in the beam. But it doesn't make any difference. You can consider in either in BC or in AB. Ultimately, the results will be the same. But I will prefer, for convenience of calculations, I will prefer it to be considered in a portion AB. So I will not show this 10 kilonewton in free body diagram of BC, and now I will adjust the free body diagram of BC. Now, since free body diagram of BC, joint C has received the balance from free body diagram of CD, and joint C is in static equilibrium, we cannot do anything at joint C now. Whatever adjustments are to be done at joint B. So let us do the adjustments at joint B. What are the rules for adjustments? We must ensure that summation of forces in x direction should be equal to 0, summation of forces in y direction should be equal to 0, and summation of moment should be equal to 0. So summation of forces in x direction, this is 4 kilonewton acting towards left, so there must be a force of 4 kilonewton acting towards right to achieve that summation of forces in x direction is equal to 0 for member BC. Remember, every joint is in static equilibrium, every member is in static equilibrium. That is what is free body diagram is. So this member is in static equilibrium. We have achieved the static equilibrium by imparting these forces at C, and we have achieved static equilibrium of the joint C by transferring equal and opposite of these forces in the portion BC. Now we have to achieve static equilibrium of member BC. Now, static equilibrium of member BC, since summation of forces in x direction should be equal to 0, I need to act this 4 kilonewton towards right at B. In that case only it will be balanced. I cannot do anything at C now. Whatever adjustments are to be done at B. Now, summation of forces in y direction is equal to 0. So this is already 0. So I am no need, but I am writing this 0 kilonewton acting downwards, okay, as a practice. And then what is the moment acting at B? Acting moment at B, there is no moment due to this 4 kilonewton at B, because 4 kilonewton do not have any lever arm with B. There is no perpendicular distance of this 4 kilonewton with respect to B, because 4 kilonewton is acting in the line BC. So principle of extensibility of force, axioms of mechanics we have seen. So in that case, this is passing through B, so there is no moment generated by this 4 kilonewton. This 0 kilonewton into 5, so moment, so force into perpendicular distance, so 0 into 5 is 0. This 16 clockwise is the only moment. Since this is the moment, we need not multiply with distance, and we should directly take it as 16. So this 16 kilonewton meter is the only moment acting at B. It is clockwise. To balance it, there must be 16 kilonewton meter anti-clockwise moment acting at B. I hope you got it. Now this BC member is balanced. My member BC is balanced. First, I have balanced member CD by balancing the forces at C. Then I have balanced joint C by transferring equal and opposite forces from CD to BC. Same forces, same joint C, equal and opposite forces. Then I will balance the member BC by arranging or by balancing the forces at joint B. Now you must have judged it right. My next step should be drawing the free body diagram of AB. My next step is drawing the free body diagram of AB. I am drawing the free body diagram of AB like this. I am drawing the free body diagram of AB like this. This is, erase it. I will erase it. It should be neat. I am drawing free body diagram of member AB. So free body diagram of member AB, let us say this is member AB. 4 meters is the length. This is A and this is B. I hope you got it right. Now this joint B is the same joint in the portion BC. Same joint in the portion BC. I have broken it, and this is the balance of the forces on joint B when I needed to balance member BC. Now for member, when I am drawing joint B in the member AB, I must show this 10 kilonewton which is acting load at B. I cannot change this. This is the acting load at B. We have decided that this acting load shall be considered either in the portion AB or in the portion BC. Acting load at the joint can be considered either in the portion AB or in the portion BC. So for the convenience of calculations, I have considered it in the portion AB. So this 10 kilonewton acting force, and then I need to transfer equal forces but opposite in direction from this joint B in the portion BC to this joint B in the portion BA. So for that, I need to transfer this 0 kilonewton acting downwards. I need to transfer this 0 kilonewton acting upwards. This 4 kilonewton acting towards right to balance joint B, because joint B is also in equilibrium. I need to transfer it 4 kilonewtons acting towards left. And this 16 kilonewton meter acting anti-clockwise, I need to transfer this 16 kilonewton meter acting clockwise at B. So this is how I have achieved the static equilibrium of joint B. So this free body diagram is nothing but balancing a member, balancing a joint, balancing a member, balancing a joint. First we balance the member from unknown to known, from the known forces to the balanced forces. Then we transfer the equal and opposite of the balanced forces to the same joint in the next member. And then we again balance the member for static equilibrium conditions, that is sigma fx is equal to 0, sigma fy is equal to 0, sigma m is equal to 0. And again we transfer the balance of the joint, whatever balance we have received on the joint, to the same joints in the next member. So this is how we draw the free body diagram of any structure. Now it's very simple. Calculation of reactions at A is very simple. Since this is 0 kilonewton, the reaction at A will be 0 kilonewton downwards. No need to draw. Now the X forces 10 towards right and 4 towards left. So net force in X direction is 6 kilonewton towards right. So to balance it, there must be 6 kilonewton acting towards left. So that 6 plus 4, 10 towards left and 10 kilonewton towards right. And the bending moment, that is very much interesting. Acting moment, this 16 kilonewton meter is a clockwise moment. It is acting like this. So this 16 clockwise, I am just showing this 16 kilonewton meter, I think, moments acting at A. I am writing the description what is doing moments acting at A, acting moments at A, and I know I should apply the equal and opposite moment for reaction. So 16 kilonewton meter, it's a moment, it will not be multiplied with distance, so 16 as it is. This 10 kilonewton meter, 10 kilonewton will create a 10 into 4, again 40 kilonewton meter. This 16 kilonewton meter is the moment clockwise. Similarly, 40 kilonewton meter is a moment that is created by this 10 kilonewton force. Remember, this 16 kilonewton is a moment itself. It need not be multiplied with distance. It is the moment, it is acting same throughout B and A, throughout A and B. So this is the moment due to this 10 kilonewton. There is one more force, this 4 kilonewton will create a moment of 4 into 4, but it will be in anti-clockwise direction. So anti-clockwise direction, 4 into 4, 16 kilonewton meter is the total force. So I can say 16 clockwise and 16 anti-clockwise will cancel each other, and then there is a net acting moment of 40 kilonewton meter clockwise at A. To counterbalance it, A must have a reaction of 40 kilonewton meter anti-clockwise at A. So this is the complete free body diagram of AB, BC and CD. And my friends, it is very clear, once we draw the correct free body diagram, it is very easy to plot the bending moment diagrams. It is very easy to analyze the structure. It is very simple to write the moment equations for the portions CD, BC and AB, which is required in our flexibility analysis as well as strain energy analysis. In our next video, we will discuss our flexibility analysis, and in that case, invariably, we need to discuss the free body diagrams. We need to draw correct free body diagrams. In our next video, we will see the flexibility analysis for analysis of structures. I hope you have liked this video. Thank you for being patient and watching this video. Thank you.